Hello everyone, Dr. Chen here. So we're going to talk about more general case of energy conservation. So we start from work energy theorem. The total work done on the system equals to the change of kinetic energy. And the total work can be divided into two parts, work done by non-conservative force and work done by conservative force. And we see if work done by non-conservative force is zero, we only have conservative force doing work, then mechanical energy is conserved. Now what's going to happen if we do have non-conservative force doing work? So what do? We're going to move the work done by conservative force to the other side. But we also discussed the work done by conservative force. Negative of work done by conservative force would be equals to change of potential energy. This term equals change of potential energy, which gives us the work done by non-conservative force equals to change of kinetic energy plus change of potential energy. And this is change of kinetic energy, this is change of potential energy. We can rearrange it a bit. We put all the final two terms in final state together. We put the two terms in initial state together. Now we find out it's quite simple and clear. If we do have non-conservative force doing work, then the work done by non-conservative force equals to this is just the change of mechanical energy, right? So, yeah. And then we define the kinetic energy plus potential energy is mechanical energy. So the work done by non-conservative force equals to change of mechanical energy of the system, which is also consistent with mechanical energy conservation. If the work done by non-conservative force is zero, the mechanical energy is conserved. If the work done by non-conservative force is not zero, then the work done by the non-conservative force equals to change of mechanical energy. So now we can introduce the principle of conservation of energy. Energy can neither be created nor destroyed, but can only be converted from one form to another. So the forms can only transfer from those different, the energy can only transfer formed from those different forms. But the net energy is always conserved. So let's do one example. It's a firework program. Starting from velocity 0, and the burning will push the firework up to a height of 29 meters, and the work done by this burning propellant is 425 joules. We want to find out what's this final speed at this height, and then the equation we need to do is energy conservation. The work done by non-conservative force equals to initial change of mechanical energy of the system. So final kinetic energy subtract initial kinetic energy. We don't have spring force in this problem, so we don't need to worry about spring potential energy. Plug in all the numbers. Work done by non-conservative force equals change of potential energy plus change of kinetic energy. Now change of potential energy is mass times acceleration g, which is 9.8, times the increase in height, and change in kinetic energy is 1/2 mvf squared, and plug in all the numbers, or can solve for the velocity to give us 61 meters per second. So this is the energy problem when there is indeed non-conductive force doing work. Then we need to use this equation. So next topic in chapter of energy, power. Power is defined by the work done divided by the time it takes to do such a work. So average power is work divided by time. So because the unit for work is joule, unit for time is second, so the unit for power is joule per second, and we also gave it a special name, watt. Now, if we apply a force on a moving object, its average velocity is v, then there's a simple way to calculate the power of the force. We know work is force times displacement, and the power is work divided by time. Work is force times displacement. And then we also know displacement over time gives us velocity. So power can be calculated as force times average velocity.